We can see now that all our delta weights are positive, and that's going to cause a bit of a problem when we load the next data row, because now this neuron it's looking at this filter location and this pattern 1, 0 and concluding that these delta weights need to be positive in order to reach a better prediction next time. But when we load the next data row, which is going to be 0, 1, 0 with an expected outcome of 0, it has to conclude the opposite, that the delta weights here should be negative to reach a better value. So how do we solve this problem? The way we do that is by adjusting these values. Basically, we just have enough of these synapses to deal with this, and you really have to play around with it for a while to get a feel for what is going on. We can already see that this weight is starting to grow more than this one, and over here too, and that's because we have more inputs associated with a positive outcome over here than the lower one. So basically, like this value, which is the top one, is has more positiveness associated with it. This CNN is actually capable of solving this particular mock task. So I'm going to run a bunch of epochs now to show you how the weights are updated and explain why. Alright, so let's run some epochs. So after 400 epochs, the batch MSC is pretty close to 0, so let's see what's going on. The 001 input is gonna have stuff going this way. So this huge positive weight is not utilized. There's a negative bias weight here that is used, and what can we see here? We can see that this weight over here is negative, so whatever positive is coming in here is actually going to contribute to something negative in the end. So that's something to think about. So for the first pattern here, it's going to be a negative input, also with the help of a negative bias weight over here. So that works, and then we have 110 with an expected 1 at the end, and then this huge positive weight is utilized, so we're going to get a really big input there, and also here. But since this weight is much bigger than this one, we're going to get a positive input over here. This weight is now actually bigger than both this one and this one. It's pretty interesting. So now we're going to look at this pattern 010 with an expected 0, and first we're not going to utilize this huge positive one, and it's going to be a slightly negative one, and then we have a really big positive one coming in here, so that's going to contribute something negative, and we get a negative value. And here we actually can see that the bias is essential, because without the bias, the positive value might have competed against the negative value here. So here we actually need the bias. I don't know exactly if it's essential in this case, but anyway, we can see that they are being used. I don't know about this weight, if it's really necessary here, but I get a feeling like this one are really helping to solve this problem. So I would say that this CNN is just capable enough to solve this. And what's going to happen if we add another data row that looks like this? Yes, you have guessed it. It's not going to work, because then we get two contradictions, not just this one, but also this one, and we need more neurons and synapses to deal with this. And that is also the case for the original data that I showed, this one. And we could cheat and fix this really easily by changing all the ones to 0.99 wherever we have the expected value being 0. So it would be like all these places would be like this. I can show you. I actually set up a data set that looks like that, like this. And it doesn't matter whether it's 0.9 or 0.999. There wouldn't be any contradictions, so this would actually be fixed. But this is cheating, because even though we might not use binary numbers in a real data set, we're still going to have to face these types of issues, but with floating point numbers. And we have to somehow add more neurons and synapses to fix this. If we just want to add more neurons and synapses and don't want to add more layers, this is normally done differently in a CNN compared to a normal ANN. In a normal ANN, we just add more neurons on the vertical axis and connect them to the inputs to create more synapses. But in a CNN, we want to stick to this intuition that each neuron represents a filter location. So then we would have another neuron like up here. It wouldn't have a filter location unless we want to extend the filter over the border here and like having an imaginary zero input that we connect to it. And that's normally how it's done. It's called padding. But the main way that more neurons and synapses is added is through something called multiple filters. So basically we just have another setup of filter synapses neurons. So we know that like all these synapses and neurons have been trained with regard to this filter, and the weights are here are the same for the filter. So then we just like add another setup of this whole configuration and connect it to the input over here. So we'll have 6 inputs here instead of 3. And since I'm lazy, I'm not going to do that in this video, but I can show you a picture of how this would look. So when I was going to draw this and looked in the literature, I realized that if we have one filter, then there should only be one synapse over here, and it should be the same kind of synapse as up here with shared weights between the 2 filter locations, but yeah, the only difference is that it's always connected here. I'll draw a picture to show you what it would actually look like. So we don't have one of these guys. And then we have a connection to, a connection up here. So this is how it should have looked. So in the previous configuration, this part was convolutional, but this part was densely connected. But now it's 100% pure convolutional, as it should be. But anyway, back to the picture I was going to draw with multiple filters. So this is a picture of 2 stacked filters. It's basically just another setup on the depth here. I'm only showing one filter here, so you can see that it's connected to this like dimmer part in the background here. And this filter then has a set of shared weights, the ones behind here. But then we have another filter with new randomly initialized weights, which are shared, and then add corresponding neurons for those, and then we'll get more weights back here too. And here is where everything gets connected, so we get 6 inputs instead of 3, and more weights that can be trained, and in the end a better capability of the network to solve different tasks. I'm pretty sure that this configuration would solve my data problem, i.e. this one. Maybe not with the last line here, or maybe if I set it to 1. But I'm not going to try that right now with my existing program, because I didn't build it for scalability with these neurons. I just built it to work with a couple of neurons and some buttons, and this part especially became really messy, like the backprop between L1 and L0. I mean, look at it. It's like embarrassingly untidy. So you really need these like tensor operations and clever data structures to scale this. It's probably smarter at this point to just start using a deep learning library such as TensorFlow or Keras. I built a small prototype in Keras. I'm just getting some error right now, but if we would try to build this network in Keras without the extra synapse here, it would roughly look like something like this. So we have a sequential model. We add a convolutional 1D layer with 1 filter size of 2, input shape. So this is where I'm getting the error. It's like it should be 3 on the x-axis and 1 on the y-axis, but something's wrong here. Activation function sigmoid. We use strides 1 so it takes one step at a time with the filter. Padding equals valid. This means that we don't use padding, and we use a bias. Then we need to apply the flattening command, which is always necessary to before a dense layer after a convolutional layer. And then we have the dense layer with one neuron, sigmoid activation function, and a bias. If we now want to see a representation of this model in Keras, we can call this command model.summary, and then we'll get something that looks like this. So we can see here that there are 6 parameters, just as in our own GUI. And if we want to do this one with 2 filters, all we need to do is to change this one into a 2 and then run it again. So Theano is the same as TensorFlow. So Keras sits on top of Theano or TensorFlow. And then also you can like optimize your compiler to work better with linear algebra functions, but I haven't done that yet. And here we get 11 parameters. It should be 12 though, right? Oh, okay, so I might have done another mistake. So perhaps there should only be one bias neuron here, because this is like considered a normal dense layer, and then maybe it should only be one bias neuron here. I'm not entirely sure, but that's what it says here at least. But I will probably make another video where I tidy this up and go through this in more detail, and also go through some concepts like pooling, dropout, pruning, maybe do this in 2D or 3D. I did try my data problem with a fully connected network as well. I can show you. So with this data set, and then it looks like something like this. So I have three neurons and one bias neuron in the hidden layer, and it cannot solve the problem when we have this last data row. But if I remove it or switch it to 1, the expected value, then it can solve it. So we can see the batch MSE goes down to 0 here. If we now compare this dense ANN with this one, I'm actually not sure which one would be smarter in this case. I mean, theoretically, a dense ANN should be capable of deducing the equivalent of a convolution on its own, somehow, theoretically. But assuming that these are equally good now, we can see certain things here. I mean, the main difference is that we reduce the number of synapses significantly here, with the idea that we propagate signals in a more clever way. And on this scale, it might not seem like a super big difference, but when we scale this to dozens or hundreds of layers, and when the weight file is in gigabytes, this has proven to be of high significance to reach better results. So with those words, thanks for watching, and sorry for the catalog of screw-ups with the biases. I'll try to redeem it in a sequel video.